if we're trying to find the weight of a mass of an object, we're going to be using the weight force formula, which is W equals mass times the acceleration due to gravity. Now, for some of these problems, it doesn't specify where it's located, so anytime it doesn't specify, we're going to assume that they're talking about an object on Earth. That does make a difference because G is 9.81 meters per second squared on Earth. We're going to round that to 10, but on other places that's not the case for G. So you do want to pay attention to if it's on Earth or if it's not on Earth. Well, for this one, we're just trying to find the weight, which is great because we can just plug in the values here then. M, the mass, is 50 kilograms. G, the acceleration due to gravity, is 10 meters per second squared. So when we multiply those, we're going to end up with 500 kilograms times meters per second squared, but that's just a force, so that's 500 newtons is our weight force. For 21, the difference between 20 and 21 is the weight of the object is given for this. So when we have W equals mg, we're now looking for the value of m. So we have 70 newtons. I know that's our weight force because they say it's the weight, and in newtons it makes sense. The units for weight is in newtons, is mass, and then G is going to be 10 meters per second squared. We divide both sides by 10, and so then we get 7 kilograms is the mass. Now 22 is different because for 22 we're talking about being on the moon. And when you're on the moon, the gravity is about 1/6 of the pull of gravity from Earth. So that value for acceleration due to gravity is 1.6 meters per second squared versus the 10 that we have on Earth. So for this one, we want to find the weight on the moon. So we have W equals mg. And we know that the mass is 50 kilograms. We know that the acceleration due to gravity is 1.6 meters per second squared because we're on the moon. And so that is going to equal, when we plug it into our calculators, 80 newtons. So this guy on Earth, this piece of iron, I should say, the piece of iron weighs 500 newtons on Earth, and it's only going to weigh 80 newtons on the moon. All right, so same 50 kilogram object, completely different weight forces. For 23, it says an object has a mass of 50 kilograms on Earth, and it wants to know what the mass on the moon would be. Well, this is the funny thing about this. The weight force takes your mass times the acceleration due to gravity, right? But that's your weight force. Your weight force is going to change. So your weight on different planets is going to be different. However, one thing does not change on different planets, and that is your mass. So here, this is a trick question, all right? If you know your mass on Earth, you know your mass on the moon, you know your mass on Pluto and Mars, on the sun. The mass not going to change. So the mass is the same everywhere. So mass here is just going to be 50 kilograms. Okay, taking a look here, number 24, it says which graph shows mass and acceleration directly proportional? Well, this is a funny problem, and the reason why it's a funny question to me is because mass and acceleration are not directly proportional. So I am going to kind of cross this guy out, and instead of this problem, I want us to consider the relationship between force and mass and acceleration. Because it does turn out that force and mass are directly proportional, and it turns out that force and acceleration are directly proportional. And what I mean by that is as mass increases, right, if your acceleration is not changing and your mass increases, your force is also going to increase. Likewise, if it decreases, the force will decrease. Okay? If we are just talking about acceleration of one object and the mass isn't changing, if you are accelerating, then your force is growing, and if your acceleration is less, then the force is also going to be less. Okay? So if I'm considering F equals mass times acceleration, if I'm trying to find a relationship or a graph if I kind of replace this guy here with force, okay, this would mean that force is directly proportional to acceleration. And then let's change this one here to force. And force is directly proportional to mass. So as acceleration increases, force increases. As mass increases, force increases. So for 25 here, we have which graph above shows mass and acceleration being inversely proportional. And what that means is as one increases, the other one is decreasing, right? So we changed A and C, so let's take a look at B and D. Here for B, acceleration is increasing, but then the mass is also, so that's not going to work. So the only graph we can have here, that inverse relationship, is going to be for D. All right, and for goal 7, we're going to determine the acceleration of a 5 kilogram cart that is pulled with a force of 20 newtons. Assume there's no friction. All right, so on your equations, right, so you'll be given these equations. I had mentioned before I would also add F equals ma. So this one's going to be given. All right, so we'll have A equals force divided by mass. Okay, and then I like to add F equals ma because this is my preferred equation, but this one is the one that's going to be given, so it's helpful to know both. So here, all we have to do is figure out what we're looking for. We're trying to find acceleration. So in this case, since we already have this equation given to us, let's go ahead and use that. So we have acceleration is force divided by mass. The force is 20 newtons. The mass is 5 kilograms. So that's pretty simple to solve for. We get 4. Now you need to be careful here because of the units. Now here it's newtons divided by kilograms, right? But you have to remember newtons is kilograms times meters per second squared. So the kilograms cancel out and we get meters per second squared. Now if you'll notice, we're trying to solve for acceleration. So if you just remember the units for acceleration, it's a lot easier than trying to cancel out units when they don't match up here. All right, 27. Miguel's car weighs 500 kilograms. And let's see here. He's trying to push a car to the gas station, and he has 0.02 meters per second squared. We need to figure out how much force that is. So this is where I like to use force equals mass times acceleration. So that's this other equation here. So our mass is 500 kilograms. Our acceleration is 0.02 meters per second squared. So that meters per second, that's the same thing here. And then we plug that in. So 500 times 0.02. And then our force is going to be 10. Now again, we have kilograms times meters per second squared. That is what a newton is. So this is 10 newtons. And then for the last one here, we have it takes 100 Newton force to move an object with an acceleration of 10 meters per second squared. So this is up to you which one you want to use, but my preferred equation is F equals ma because it's really easy to solve for any one of the missing variables. So let's go ahead and plug in. We have 100 newtons here. We're looking for the mass, so I don't know that. And the acceleration is 10 meters per second squared. So as you can see, if we're trying to solve for m, it's really easy to identify that we need to be dividing by 10 to do that. So we get 10 equals the mass, and the units for mass are going to be kilograms.